Hi again, this is the pre-class shortened version of the lecture to prep you for the discussion of descriptive statistics. This is what we'll talk about today. We'll talk about descriptive statistics. We'll compare them briefly with inferential statistics. We'll talk about a univariate analysis because that's a part of the process. We'll talk about measures of distribution, which are primarily frequency histograms and frequency distribution. We'll talk about measures of central tendency, which are mean, median, and mode. And we'll talk about measures of dispersion, which are range, SemiInterquartile range, but more commonly, standard deviation and variance. Descriptive statistics are simply ways that we use to characterize data from a univariate analysis. And I'll define univariate analysis in just a second. Descriptive statistics typically include something about the distribution of the data, the central tendency of the data, and or the dispersion of the data. Dispersion is a measure of the variability. Inferential statistics are different from descriptive statistics because, in contrast to descriptive statistics, inferential statistics make comparisons in the form of probability statements comparing two or more samples of data. We did a couple of those in class last week, but classic inferential statistics include the chi-square, Mann-Whitney U-test, ANOVA, t-test, things like that. We really won't focus on inferential statistics in this class. This class is about descriptive statistics. Again, descriptive statistics are going to be using a univariate analysis and talk about distribution, central tendency, and dispersion. But before we get to those, let's talk about univariate analysis just briefly. It simply involves the examination across cases, multiple cases of a single variable. Usually there's a range of scores along the same measurement axis. For example, what we did in class last week, we measured everyone's height in inches. We did it after class. If we had measured most of the people's height in inches, but one student was measured in millimeters, that would not be a univariate analysis because we're not using the same scale for everybody. Essentially, in order to be a univariate analysis, you have to have multiple measurements along a single measurement scale. And the example we'll walk through today, in this video, is the pre-pharmacy GPA of all the P1 pharmacy students from the fall of 2013, so last year's class. So here's, on the right-hand side is a list of GPAs of all of the incoming P1 students last fall. I excluded the Health Pro Start students because they were not that information wasn't provided. This data is univariate data scale of measurement because basically all the numbers come from the same measurement. They're GPA values. The top is 4. And essentially they are from a univariate scale. So what's the scale of measurement? Is it interval, ordinal, ratio, nominal? Well, it's an interval scale. Although, as I said before, it's derived from ordinal data, so it's a little funky. But it's still an interval scale of data. So descriptive statistics are about summarizing the data. So how can we summarize the data? Well, one way we could summarize the data, we could say, there it is. There's your, whatever it is, 91 values, 90 values right there. That's your summary. Well, that's kind of a busy thing. And if it were even more than 90, it'd be even busier. So listing all the data is not the best way to summarize it. And that's really what descriptive statistics are all about. They're trying to help you visualize the full data in the sample or full data in the data set without having to see every individual value. So how could we summarize it? One would be a graphic way, and that would be with frequency distributions and frequency histograms. So we'll go to that next. So a frequency distribution is a summary of the frequency of individual ranges of values, individual values or ranges of values for a variable. The simplest distribution would list every value of a variable and the number of cases who had that value. More often than not, frequency distributions take a sort of a range or a clump of values and put them together. You can do frequency distributions as a table or as a graph. If it's in a graph, it's called a frequency histogram. Here are a couple of examples of frequency histograms. The one on the left has the GPAs divided by 0.05 increments. So 2.95 to 3, 3 to 3.5, 3.5, 05 to 10, 3.10, 3.10 to 3.15, yada yada, on the left-hand panel. The right-hand panel has the GPAs with broader ranges from 2.8 to 3, from 3 to 3.2, from 3.2 to 3.4. And what's plotted as the column heights is essentially the number of students that have GPAs that fall into those scores. Now, from that, we've depicted the values of the 90 students who we had individual scores from, and this is a bit of a summary. You don't have all the individual data, but from these histograms, you can sort of get a sense of, yeah, I think I know what the values look like. I think I know what the distribution kind of look like. Well, maybe you don't like graphs. What if you couldn't draw a graph? How would you summarize that data verbally? That is the 90 values. And that's what probably the main focus of the rest of today's discussion. How would you describe the data, the 90 values that are there? Typically, people provide some measure of central tendency, and they provide a measure of dispersion or variability of the data. So let's talk about central tendency first. Central tendency essentially says this is something about the center or the middle of a distribution of values. The three major types of estimates of central tendency are the mean, the median, and the mode. The mean is the average, the arithmetic average. You add them all up and divide by the number of samples. The median is the 50th percentile. So from the perspective of the median value is the one where half the values are higher and half the values are lower. It's not always equal to the mean, but that's what the median is. The mode is simply the most frequently occurring score. There are different requirements for calculating different measures of central tendency. For example, and we talked about this last week, you have to have at least an interval or ratio scale of measurement to calculate the mean legally. And you need at least ordinal data for the median. If you don't have interval data, you cannot calculate the mean. Legally, you cannot. This shows the mean, the median, and the mode for that distribution of data. I won't go through all the detailed math, but you could work through it. The mean of those 90 values turned out to be 3.63. The median was 3.71, and the mode was 3.77. They're not exactly the same value, but they're pretty close. This just shows a depiction of it. Again, this is the frequency histogram as the background. It's a little curve that's been sort of arbitrarily drawn by the computer. And you can see that the mode is 3.77. And that's a little bit higher than the median, which is 3.71, which is a little bit higher than the mean, which is 3.63. So we're back with our data. And we're asking the question again, how do we summarize this data? Well, one way is the full list, boring. Another is a frequency distribution using histograms, and we talked about that. What if you don't want to look at graphs? Another is central tendency. But central tendency is only one way to sort of look at it. That gives you sort of the center. But what if you want to know something about the dispersion of the data? And there are several ways to describe the dispersion of the data. The dispersion, what I mean by the term dispersion, is the spread of the values around the central tendency. There's no measure of central tendency, no measure of dispersion for nominal data, because you can't arrange those values by ranks. For ordinal data, ranked data, the most common measure of dispersion is called the SemiInterquartile range. So if the median is the 50th percentile, the SemiInterquartile range essentially goes from the 25th percentile to the 75th percentile. So it's the 50th, it's 50% of the data centered around the median, if you will. It's the SemiInterquartile range. It's the range of values centered around the median that will include 50% of the data. This just shows how to do the, essentially, or what it would look like for the SemiInterquartile range. The 25th percentile is 3.45, and the 75th percentile is 3.85. So basically between 3.45 and 3.85 in this range of data, you captured 50% of the values. But we want to do a little bit more, and so with interval and ratio data, that we've got, like I say, we've got more options, and variance and standard deviation are really our main options. So there's a mathematical formula that's you could probably commit to memory. You don't have to, but the variance is the sum of the squared deviations from the mean divided by n, or in some cases n minus 1. We'll get to that difference in just 1 second. And the standard deviation is defined as the square root of the variance. So the variance is the sum of the squared deviations from the mean divided by n, or maybe n minus 1. So what's up with this n or n minus 1 issue? And that really comes down to the issue of what's called samples versus populations. We'll try to spend a couple minutes on this now. We'll talk about it more in class. So there are populations and there are samples. By definition, populations are all of the values. Because they are all of the values that you're interested in, you can be certain of the calculations of dispersion. If you have all the values, you know that you won't miss anything, and whatever you calculate is accurate for all of those values. By definition, samples are really only part of a population that's been measured, and most of the time we deal with samples, to be honest. When we take 20 students out of the class and we're using them to reflect the whole class, that's a sample. When we take the whole class and we're using that whole class to reflect sort of all of the P1 students in all pharmacy schools in the U.S., that's still a sample. Because samples don't include all of the possible values. You can really only estimate dispersion of the population from the calculated dispersion of the sample. You sort of think that the sample reflects the population, and so you use the variability, the dispersion in the sample. You say, well, that's probably a pretty good estimate of what the variability would be in the population. But you want to be slightly more conservative, and so that's why you divide by n minus 1. Because if you divide by n minus 1, you get a bigger number. Because you're making the denominator, the bottom part of the fraction, a smaller number. On another level, n minus 1 represents what's called the degrees of freedom, the DF. And we'll talk about this concept more in class. But basically, so if we've got these data, again, we've got the 90 values. If it's a population, populations use what are called again, that's all of the values. Populations typically use Greek symbols. Instead of an X bar, the population symbol is mu, the Greek letter for M. The standard deviation is sigma. When you have only a sample, you use the non-Greek symbols, like the mean is the X bar and the standard deviation is SD and all those kinds of things. And again, the main difference is that when you're using a sample, you're trying to estimate information about the population, and you don't know what that real population is, so you try to be conservative, and so you make a calculation using n minus 1. N minus 1 is sometimes called the degrees of freedom for that sample, and we'll talk about that term later. But essentially it gives you a slightly larger value. So if you do the math, doing measures of dispersion with interval data, if you use what we did with the grade point averages, the variance is the sum of the squared deviations divided by n minus 1, or divided by n. So what does that mean? Well, if somebody has a 4.0 GPA, and the mean was 3.63, so what's the deviation? It's 4.0 minus 3.63. That's the deviation. Square that. There's another person with a 4.0, and the mean was still 3.63. Square that. Add up all those and do that 90 times, so you get to the bottom of the heap, and you got a 3.10 minus 3.63. Square that deviation. 3.09 minus 3.63. Square that deviation. So you've done that 90 times. Sum of the squared deviations from the mean divided by n. which is 90. And essentially, that works out to, this is 0.37, this difference there, that's squared, 0.37 squared, yada yada. And you do all that math, it works out to a variance of 0.0609. If you take the square root of that, the square root of 0.0609 is 0.2469. You can do all that math if you want. That is the way to calculate variance if those 90 values reflect the population. If, on the other hand, those are sample, we're more interested in P1 students in general, not just those 90 students. You go basically about through the same math. You do the sum of the squared deviations from the mean divided by n minus 1. So all this part is the same, divided by n minus 1. So the variance is slightly bigger, 0.0616 versus 0.0609. The standard deviation is still the square root of the variance. Square root of this 0.0616 is 0.2482, which is slightly larger than that value. This is not a huge difference, but this is the difference between using a sample-based calculation of dispersion versus a population-based sample. Population-based calculation, excuse me. So what could we say about these data if we tried to summarize it? We could say we've got the median, we've got the semi-interquartile range, we've got the mean, we've got the absolute range, which is 0.91 because the highest score is 4 and the lowest is 3.09. We've got the average deviation. You could do that and it would be 0.22, but people don't use those very often. We've got the variance, which if you call it a population, it's 0.0609. If you call it a sample, it's 0.0616. And we've got the standard deviation. And all of those essentially are ways to sort of summarize this so you don't have to look at all these numbers. So let's try to pull out of it just a little bit and try to summarize it. So really what we're talking about with descriptive statistics is they're a shorthand way to describe the data in a sample or a population. They're either frequency distributions, some measure of central tendency, and or some measure of dispersion. Quite often they're paired together. So if you've got this is the issue. We've got 90 individual scores. Can't we give a summary of those 90 scores? What would work as to provide us a summary? Well, we could do this frequency histogram. And that gives you some sense of it. You don't have to look at 90 individual values. You just sort of look and say, well, it looks like the average is pretty close to this. And there were a lot of 4.0s, and the lowest one was clearly in the 3.0 kind of a range kind of thing. But you don't have too much precision, but you sort of still have an idea that most of the P1 students last year had GPAs between 3.2 and 4.0 by far. But maybe you want to have a little more precision, or you don't want to look at it from a graphic perspective. And this is sort of the heart and soul of what descriptive statistics are. You can either, when I asked Dr. Wilhelm, can you tell me something about the GPA of the incoming P1 students last year? She could either give me a piece of paper with that, all the individual values, or she could say, well, there were 90 of them. The mean was 3.63, and the standard deviation was 0.25. And from this information, I kind of conjure up in my own mind a picture of distribution of data that kind of looks like that. Not exactly like that. I don't know the exact individual values, but I have a general sense that there, a lot of them, there probably aren't a whole lot of 2.5s in that with this. My experience tells me that if the mean is 3.63 and the standard deviation is 0.25 and the sample size is 90, I sort of in my head sort of create a picture that says, it might look a lot like that. And this is a cleaner, tidier way to summarize that data. And again, you might as well just summarize this data, because this data is really not in most cases, the descriptive statistics about a sample is not even all that. It's not the be-all and the end-all, because what you have from a sample, the purpose of a sample is to try to get information about the population. So that's a bad digression. So what have we done today? We've essentially talked about descriptive statistics and compared and contrasted them to inferential statistics. And again, all of this discussion has to take place on a univariate analysis where there's sort of one measurement scale, but most of the time that's the case. We've talked about measures of distribution, frequency distributions as a way to summarize a group of data. We've talked about measures of central tendency as a way to summarize data. We've talked about measures of dispersion as a way to summarize data. And we've talked a little bit about populations versus sample and degrees of freedom. And we'll talk more about all of these concepts when we come to class on Thursday. Thank you very much.